Hi, my name is Jaylin Herskovitz. I am a PhD student at the University of Michigan, and today I'll be presenting my paper, Making Mobile Augmented Reality Applications Accessible. Augmented reality, or AR, enhances our capabilities and experiences by overlaying virtual information onto the world around us, and AR is becoming more popular for a variety of use cases. Here I show two examples. On the left is IKEA Place, which lets the user see what furniture would look like in their home, and on the right is Statue of Liberty, an educational AR app. However, AR content is often primarily visual and exposes neither the semantics nor the interfaces that would enable it to be accessed by accessibility services such as screen readers. If I open these apps while using a screen reader, I may be able to learn what buttons are on the screen, but I can't learn anything about the AR content or how it's placed in my environment, rendering the app useless to people with visual impairments. Prior work has considered the similar topics of virtual reality accessibility and the potential to use AR technology as an assistive tool to make the world more accessible. Our work draws inspiration from both of these areas, but instead focuses on existing AR app accessibility. Our approach consists of three main parts. First, in order to understand how to make AR apps accessible, we performed an analysis of the functionality of existing AR apps. This was done with the goal of uncovering common tasks in AR in need of accessible counterparts. Second, we developed prototypes of non-visual alternatives to three common tasks that we identified to act as design probes. Finally, we conducted a study to explore how 10 blind participants interacted with AR on mobile devices. For our analysis of existing AR apps, we collected all apps that were featured on the App Store over a 3-month period. This resulted in a set of 105 apps across various categories. 3 members of the research team performed a thematic analysis of this dataset, coding each app for the AR tasks or operations that were required to use it. From this analysis, we formed 5 broad categories of AR tasks. Establishing physical virtual correspondence, which includes tasks necessary to establish AR tracking. Creating virtual content, which includes different methods used to place content in the space. Observing AR content, which includes tasks that allow the user to gain information about the look of virtual content and its layout in the space. Transforming virtual content, which includes moving, rotating, scaling, or deleting content. And finally, a category which we called activating virtual content. This is a broad category which includes any task where a user selects an object in the scene, and this may result in additional effects such as the object changing state to become editable or an animation playing. From this analysis, we also quantified how common certain component tasks were. For example, in the category of establishing physical virtual correspondence, scanning the environment generally to establish tracking was the most common task, but other tasks such as requiring the user to scan a specific object were also present. In the category of creating virtual content, placing content on a physical surface was the most common task, as opposed to other methods like placing content in midair or drawing with a finger. We then prototyped non-visual alternatives for 3 of the most common tasks identified in our analysis: 1 for scanning the environment, 2 for placing content on a surface in the scene, and 2 methods for finding the location of virtual content in the scene. Next, I'll describe how each of these worked. Our scanning app provides progress updates through VoiceOver when the user scans new surfaces and periodically updates them on the surface area scanned.
Walk around the room and slowly pan the camera to scan. New horizontal plane found. New horizontal plane found.
The camera-based placement method uses the phone's location to determine the location of the virtual object to be placed. As the user walks around the space, the virtual object follows the phone and is placed on the closest surface to the user.
You are now holding a vase. Vase moved to a new surface. Confirm.
In the guided placement method, the app generates candidate positions for an object based on the available surfaces and then asks the user a series of questions to place it.
Where would you like to place the object? On the floor. Button. Where on the floor? In the center. In a corner. On an edge. Button. Face the edge that you would like to place the object on. Then press the confirm button below to place the object. Confirm. Button. Confirm.
Next, for camera-based search, the app provides verbal feedback about the objects in the room as the user pans the camera around the space.
Found blue chair 1.6 meters away. Left blue chair. Found purple vase 0.6 meters away.
And finally, for guided search, the user first selects an object from a list of all the objects in the space and is then given verbal directions to its location.
Objects. Gray chair. Pink. Black chair. Button. Black chair is 1.1 meters to the right. Black chair is 1.0 meters to the right. Black chair is 0.6 meters to the right. Black chair is 0.4 meters in front of you.
With these constituent tasks, we then created 2 apps that combine them into full AR experiences. These are meant to mimic common existing AR apps, so we had a furniture layout app and an educational solar system app. Now for some details about our evaluation. We ran a user study with 10 participants, 8 who were completely blind and 2 with low vision, where they were asked to use each of the apps mentioned previously. We evaluated each individual prototype separately with short tasks, and then evaluated the apps that combine these with open-ended use. Because participants used all of our prototypes, we can compare the methods that we developed for the same task. So, between the placement mechanisms, participants generally preferred camera-based placement because it gave immediate and continuous feedback about the placement of an object. While guided placement was usable, it lacked semantic information and precision. Then between the search mechanisms, participants strongly preferred guided search, as using camera search to scan the room for unknown targets in our task could be tedious. However, this effect could be mitigated when participants were familiar with the layout of virtual objects, for example, when they place them in the space themselves. This is something that could also vary based on a participant's level of vision and how long they have been blind, as they may understand the space differently. This is something that we discuss more in the paper. In general, we observe that accessible interactions with AR need to not only provide continuous and meaningful feedback, but also mixed descriptions of both physical and virtual objects. Participants requested information on the physical objects around them for a variety of purposes, including as guidance to help them locate or manipulate virtual objects and to more easily navigate the space. In the future, research should engage more with visually impaired people and other populations to work to design accessible AR that is not only possible, but usable and desirable. This could potentially involve using other output modalities such as spatial audio or haptics. Finally, technical advances in providing semantic descriptions of a 3D space and answering complex layout questions are needed in order to advance accessible interaction techniques. We also discuss more opportunities in the paper. Overall, this work demonstrates that AR can be made accessible to blind users and sets a roadmap for future work in that direction. Our design probes and evaluation show that providing continuous feedback is extremely important, as is mixing descriptions of the virtual and physical objects to make the entire AR scene understandable. Thank you.